Hello, my name is Vitek. I'm a professor at Northeastern University and Czech Technical University, and this is my talk, R Melts Brains, or How I Learned to Love Failing at Compiling R. The talk will summarize the last 10 years of my research, where me and a group of students and postdocs and researchers have been attempting to take R programs and compile them to machine code. This talk is in 3 parts. The first part focuses on performance. And here I want to explore what it means to be slow for a programming language and motivate why we need compilation. So you may have heard someone tell you that R isn't slow because all of the built-ins are written in C code, and that C code is compiled to optimize machine code. Ergo, R is fast. While this is true, it is deceptive. And I'll try to explain it by separating our operation into what I call micro operation and macro operations. So micro operations are the operations that you will find in any programming languages. They are function call, assignment, addition, looping constructs. In R, they are much slower than in traditional languages like C or Java. In those languages, these operations are as simple as possible because the goal there is to be able to string as many of these operations together at almost no cost. In R, things get much trickier. So I'll just give you a little taste by walking you through function calls to start with. In Java or in C, a function call is not much more than moving arguments into registers and jumping to an address. In R, the first thing we have to do is locate the target of the call. This is identified by the name of a function, say f here, which we have to look up in an environment. And this is using the symbol, the function's name, doing hash lookup, getting a pointer to a function. Once we have a pointer to a function, we need to create an argument list. Since we don't know in which order the function wants its arguments, what we have to do is create a linked list that will contain 1 link per argument. Each name that we see at the call site will be remembered, so we can match them with the parameters. Expressions are going to be packaged into promises, not evaluated, and those promises contain the code of the expression and a pointer to the environment, so here, so that I could resolve A and B. And then, once we call the function, we will match the arguments and the parameters, traversing the linked list and reordering the elements so that they are in the right order. And then we can call the function. This is much more work. It requires allocation, eventually deallocation, list traversal. It's quite involved. Assignments. Assignments traditionally in normal programming language would be moving a value from a register to a memory location. In R, we have to first find the left-hand side of the assignment. This may involve hash environment lookup. We have to force the promise on the right-hand side if there is one, and that means evaluation and everything. And then if we find out that the value that we're assigning is going into a shared data structure, we may have to duplicate that data structure, so copy the vector we're writing into. All of that is done for every assignment. Addition In C, addition is done by the hardware. It's hardware operation. You add two numbers and you get the result. In R, both values are always heap allocated data structure. So you have to check their type to see if they're compatible. You have to potentially convert one or the other into the right type. You have to make sure that they have the right length or be ready to recycle, and then perform pointwise addition while checking for NAs. So all of this is again quite expensive and costly. Lastly, while loops. Well, while loops are no different or special. They're just stringing together many of these micro operations, adding up all of their overheads. That's on the micro side. On the macro side, you have all of these fairly complex operations like column means or vector addition that are indeed written in C, but which the R implementation cannot globally optimize. So for instance, in these two lines of code, I will allocate one vector for the result of call means. I will allocate one vector for the range of 1 to 200. I would allocate another vector for the results of adding the output of call means to the range. And then I will allocate one vector for the addition of y to y. So that's 4 vectors that I had to allocate. Whereas if I was doing this, say, in C, I could reuse the same vector and I could combine the allocation or the creation of the range with the addition into one pass. So I could have fewer data structures and fewer traversals of those data structures. So what does this mean? It means that there are good reasons why R could be slow, both if you're using micro and macro operations. Now, the question is it? And for this, we need to think about what is performance in a programming language. And that is quite tricky to measure. So here is a slide that I got from Mario Volchko when he was teaching a class on interpreters at Stanford. And basically what he was trying to do was take a number of small program algorithmic tasks written in multiple programming languages and try to see the relative performance. We understand that this is not a scientifically satisfactory way of comparing programming languages. Most importantly, because these tasks are not tasks anybody cares about. If you want to do a meaningful comparison, you have to have a problem you care about and implement it yourself the best way you can in the various languages, and then you can compare how fast they run, how easy it was to write. But this is as good as it gets, and it gives us some idea. So what this graph shows is the performance normalized to C. So if all languages were at the same speed, they would all be 1, and the axis is on a log scale. So what we can see here is that languages like C and Java and even JavaScript to some extent are performing reasonably well. JavaScript has some performance issues, but languages like Perl, PHP, and Python, which as it happens are all 3 interpreted languages, not compiled, run much slower. They run, close to 50x slower than C. with some peaks above 100 times slower. What would be a good target? Well, a reasonable goal would be between 2 and 5 times slower. I think that would be an acceptable performance cost for most tasks. There will be tasks where even that is too slow, but for many tasks it's probably fine. So how does R fare in this picture? So we took the same programs. Here they have been given shorter names, and we compare them to Python and C. So this is again normalized to C code, and the blue is Python. So you can see it sort of varies. Some between the average slowdown seems to be around 50x, and unfortunately R here is closer to a 500x slowdown from C. So these numbers, I should say, were obtained using the GNU-R AST interpreter. So this is an older interpreter. The data was obtained in 2010. I'll show you some newer number with the bytecode compiler. But they're interesting because they show how bad things get when the programs you write mostly consist of micro operations. Because all of these tasks are very algorithmic tasks for which R is not ideally suited. All right. So the next bit is I want to look in the next experiment. I want to look at more traditional R programs. So I said previous slide was algorithmic tasks, which are typically not what you would use R for. So what would be more representative? So what we did is we took 100 vignettes from Bioconductor, which had substantial computational time, and we analyzed and itemized the time spent in different parts of the program. So what I'll show is I will show you these bars. Each of these bars add up to 100% of the execution time, and each color represents the percentage of time spent doing a particular thing. So I'll focus only on a few of them. The first here you can see the red color is built-in, so this is the time spent in a built-in. Then externals, so this is also C code but written in a package. And then the other costs are more internal to the programming language, like looking up variables, duplicating vectors, allocating consel for linked lists, and reclaiming memory. So what should we expect? Well, if it was the case that R is mostly used for macro operations, we'd expect that all of the costs, 90%, would be split between built-ins and externals. Anything else is language cost. And even if we had 100% built-ins, there's still the issue that I mentioned, which is the fact that a sequence of built-in may be slower than if one could fuse those built-ins together. So what is the picture like? So here, each of these lines is one of our vignettes, and what you can see is there are fairly large colors of light blue. That means these are vignettes that are mostly executing package code, probably in C. There are substantial red bars, and these are vignettes that are executing mostly the built-ins. But there's quite a lot of other stuff going on. So I'll focus, for instance, on the memory management part. So this is the same graph where I remove the built-ins and the external, and I just showed you the cost of memory management. You can see that the cost is, between is about 25-30% average of the execution time, and it can go all the way to 90% in some pathological cases. So what that means is 90% of your execution is just allocating vectors, duplicating and reclaiming them. These costs, we believe we can reduce a lot. Why do we think that? Well, I'll show you the next slide, and I think it'll make it quite clear. So this is for that small suite of program, a comparison of how much memory the C implementation requires, and it can vary here between about 10 megabytes all the way to close to a gigabyte, and the memory used by R. So blue is C, they're the lower bars, and R is red for the data part, and you can see that every program allocates about 10 gigabyte. The axis is again in log scale. So R allocates much more data than C on average. And this is explained by this fact that all of these macro operations that I string together keep creating new vectors and never reuse them. But the other thing to note is the green bars. They are the internal bookkeeping data that the interpreter maintains. And these are even bigger than the user data. These are things like the promises objects, the linked list of arguments in function call, and so on. So together, this means that R is using massively more memory, and one could think that for the computational task, there should be a way to get much closer to what C required. So another thing that you may have heard is, well, why bother compiling R? Because my code runs fast enough. And yeah, it is true that most tasks that we run are, pretty fast in R. So you'll wait a minute or two. There are some codes that run days, weeks, but these are fairly rare. Well, mostly because who wants to wait days and weeks? What they'll do instead is, if they ever get to the point of performance troubles, they will the programmers will learn C or C++ and recode the critical part of their algorithm in that language. So to illustrate this, let me show you call means that I mentioned a bit earlier. Call means is a function that computes the means of any kind of vector in R, and it is written in R with the following code, and I'm not going to explain it more than mention that at the end it bottoms out into either one, or if you're calling with a complex, two internal calls to call means. And these .internal are calls to the C function that actually does the heavy lifting, because this is where the looping happens and the micro operations would be too costly in R. So let's dive deeper. So this is the code of call means implemented in C. It's the do call sum function. And without spending too much time, I'll just say it looks like this, there's some startup code that extracts the arguments, and for that you have to understand the C API of the R interpreter. Then there's some code that does sanity checking, making sure that things are as they should and of the right type, and throwing reporting errors if they're not. And then there's a big switch that that tests the type of the value and has different cases for the different data types. All of that bottoms out in this gray part, which is the actual computational loop. That's the one that does all of the work, and this is the reason why we really did it in C, to be able to write this. And then after that, the code gathers the result and returns it. Okay. So if you think about this, what you had to do is, in order to be performant, you had to write some R code, some C code. You have to know how to glue them, how to make them interface. Wouldn't it be nicer to not have to do that? If we had an R compiler, we could do it. Actually, if you used the Julia language, you could write this function, which does exactly the same. It deals with all the data types R does, it deals with missing values, and it fits in one page, and in some cases runs even twice as fast as the C version that we just saw before, because we don't have to do call sum twice. So what is the takeaway here? The takeaway is that R is slow for fairly good reasons, and while the speed may not affect you, it prevents you from writing new algorithms that are computationally more intensive. And that's the point why we want a compiler. All right, and now for the second part of this talk, failure. So failure is often more interesting than success because more lessons can be drawn. I've been trying to compile R for 10 years, since 2009. It was originally intended to be a 2-3 year project, and I would move on to the next language, but it didn't happen that way. So why is R so hard to compile? Originally, R was designed to be a dynamic language, and the designers of R most likely were driven by what was easy to do in an interpreted context, in an interpreter, and chose features that made sense for them in that context, and created quite a few challenges for us compiler folks. So generally, a compiler wants to know things ahead of time. There is this separation of stages. We look at code, the compiler analyzes a piece of code, and then emits a machine representation of that code. And in order to do that, it has to know everything about the code. So for instance, it has to know where variables are. Are they in machine registers or on the stack? Well, with R, this is not possible. So for instance, this funny piece of code here has a function, f, that is a nested function of an enclosing one. And in that function, we use two variables, x plus y. And the question is, where should I find, if I'm a compiler trying to compile f, the definition of y, and where should I find the definition of x? So definition y is kind of easy because there is, at the point where I compile f, there is no definition of y, so if there will be one, it will be at the top level. Whereas the definition of x is trickier because depending on control flow, depending if A is true and the branch is taken and we assign to x, x can either be found in the enclosing function or at the top level. How can a compiler generate efficient code for this? Well, it can't. It has to leave code that will do name lookup. Look at the second line in this slide. Here we have a function f that prints twice. It has two arguments and they're both calls to prints of 1 and 2. And one would expect in most languages that we will print 1, print 2, and execute f. In R this is not the case. When we execute f, we will first execute the print of 2, because that's bound to variable b, and b is evaluated first, and then do the print of a. So this is an example of laziness. R does not evaluate argument unless it has to. We've looked at it carefully. It's actually not used much, except for metaprogramming, but it has performance and compilation implications. This example shows that function g has a variable x and maybe it stores a secret, then it calls f. That local variable is completely visible to function f, which can walk the call stack and grab its value. And lastly, no, it's not actually not quite lastly. This is just a weirdness of our function f has two uses of the variable of the identifier c. One is in function call position and it calls the function that constructs a vector, and the other one is as a variable and it binds to the parameter c, and R deals with that. A compiler may have a harder time. And as an even weirder example, here we define a function bad that deletes C from its parent environment. We call f with a call of bad as argument. Once that promise is evaluated, it will delete C from the environment, and the addition operation will try to add a vector to a function, and that will fail. Needless to say that this is not something a compiler can deal with. So that's the situation, and here I'm trying to summarize it by saying that if you think of the blue cloud as the function we're trying to compile, the problem we're facing is it is operating in an unknown environment. The function is getting some promises and is calling other functions, and either one of those promises or one of the function it calls may use reflection to change anything. So basically a compiler is unable to do anything in R because there's always that potential for the world being redefined under your feet. To give you a feeling for the state of the world in R implementations, there's a bunch of them out there. GNU-R is the standard and default one. It is fully compatible and written in C. And other notable ones are PQR, which is the work of Radford Neal, and it's a highly compatible interpreter that has a number of really neat tricks that give it good speed-ups. But it remains an interpreter, so there's a limit to how fast it can go. There was a system called CXXR that was briefly worked on by Google but was dropped. TIBCO has a cleanroom reimplementation of var called thur, and that is written in C++. There used to be a GPU version of R called Riposte from Stanford, but that has been abandoned and never was fully compatible. Oracle has a system called FastR, which I worked on, and I'll tell you more about. And this one is written in Java, and there's the Rengine system that is also written in Java by bdata-driven. None of these systems is at a state where it has all the compatibility you would want and the performance. So currently GNU-R is still the default implementation. So let's go to my failures. So it's a bit of a sad story. The first attempt to compile R was in 2009-2010. Back then we used a system called VMKit. VMKit was a framework built by researchers in France, which was on top of LLVM at the time, and it provided a Java virtual machine built on top of LLVM. And our thought was, well, if they can build a JVM on top of LLVM, we should be able to build an RVM on top of it. And we started, developing some code, but that project was scuttled when a better funding opportunity arrived. Sadly, scientists are subject to the vagaries of funding. So that leads to the second failure. So the second failure is a system called FastR. So in 2010, we were contacted by researchers at Oracle Labs, and they were working on a technology called Truffle and Graal, and they wanted us to build an implementation of R that would use Truffle and Graal, and eventually that would run within the Oracle database process, so you would be able to access data without copying. And at the time, and Truffle and Graal were sort of a technology that was integrated into a Java virtual machine. At the time, they were not ready to handle the complexities of R, neither Truffle or Graal. And what we ended up doing is writing an interpreter for R written in Java on top of a JVM. And we came up with a number of interesting optimizations that allowed us to make that faster than GNU-R's implementation. Eventually that was transitioned to Oracle, and Oracle rewrote it all to use Graal and Truffle, and now they have another system that is called FastR, which is vaguely related to what we did, faster and more complete. But let me just tell you what our experience was. So the one thing that we had to do moving R to a JVM is we had to re-implement quite a lot of code, because calling C code from Java is not efficient and you can't optimize it well. So it was really important for speed that we rewrote many built-ins, especially the simple ones, in Java. And that turned out to be an incredible nightmare. Because we realized that not only those built-ins had to be looked at, but pretty much any library that was doing non-trivial operations potentially would require inspection and maybe changes. And that slowed us down, tremendously. And what it meant was during the time we worked on it, we were never able to run real R code. We could run small benchmarks that were using only micro operations, but as soon as we were getting to things like ggplot, well, compatibility errors prevented those programs from running. So the failure here was one of not appreciating the complexity of the R environment and how everything is intertwined. So it's not just a matter of getting an R interpreter, but you have to have enough of the environment to make this work. We did have some interesting technologies, some sort of some ideas that were worth sharing. So the way our interpreter worked was it would take source code, and we had written our own parser and a small Antler parser that would take the code and translate it into an abstract syntax tree in Java. So rather than having our SX to represent code, we would have Java objects. And then inside of the JVM, we had an interpreter that would take these objects, this representation of the R code, and interpret them. So for instance, here I'm showing a call to a function f with 3 arguments. Then that would be represented in our VM as this node f that of type generic call, and with 3 sub-expression nodes that contain the 3 sub-expressions. Nothing too fancy. But the interesting trick we were playing is, as we were running, we would rewrite these abstract syntax trees to optimize them. So in the default case, you don't know what f is going to do. But say you run this once and you find that f is bound to this function here on the right. Well, then you can rewrite this call into a positional call, one that doesn't have to do the argument juggling, that knows that the arguments are in the right order. And you need to put a guard that says, is f or still that function? But once you do that, you have rewritten your slightly less efficient abstract syntax tree into one that runs faster. And we did that consistently and throughout the execution, rewriting the abstract syntax tree to replace the slow micro operations with faster ones. Another key trick we had was the notion of views. So here I'm showing a statement where I assign to variable a the result of adding b plus c, and then later in the program I multiply a by 2. So what we were doing in FastR is we would delay all of this, not evaluate those statements until we needed it. And instead we built this expression tree. Here it shows that the O variable points to a multiplication node, that points to an addition node and to the constant 2. And the advantage of doing this is, once we needed the values, we could look at this expression tree and evaluate it efficiently, fusing operation together, because you had the context. We didn't need to allocate local temporary objects, so that was a way to sort of speed up execution by a lot. There's a number of other tricks. It was a fairly involved and interesting system. The end result here is the same benchmark, we could show that running them on top of a Java VM with our Java interpreter without any compilation, we were getting on average about 8.5 speed up over the old GNU abstract syntax tree interpreter. And here this graph shows lower is better, so the lower is the faster, and the blue is the time taken by FastR. The green is the time taken by the bytecode, the GNU-R bytecode interpreter, and 1 is the time of the AST interpreter. So you could see that we were getting good speedups from a variety of sources. But compatibility was too hard for us, and eventually we gave up that project. We stopped because it was clear that on an academic time scale and budget, there was no way we could finish this effort. Since then, Oracle has spent quite a lot of effort and they have gone much further. So I haven't used their version of FastR recently, but I know that it's faster, a lot faster, and it has much better compatibility. But it's still not completely backwards compatible with R. And then I'll get to the third failure. So we took a year of rest. 2015 was, I didn't do any work on R. I thought of other thoughts. And in 2016, we started again. And there the idea was, let's build our own LLVM. And so we created a system called Reactor. And the idea of Reactor was we would only replace the compiler part. We would keep all of the rest of R intact, all of the libraries would have no changes. So this way we wouldn't have those problems with re-implementing. We would be fully backward compatible. And just replace the GNU-R bytecode compiler. And it was not a bad choice overall, but we made one key mistake, which was, and this is a very technical point, is we chose to use LLVM's intermediate representation as the representation where we make optimization, on which we make our optimizations. And it turns out that this was a key mistake. And the reason is that LLVM IR is much too low level for the kinds of optimizations we need to do for an R program. Once we sort of had translated the code to LLVM IR, to detect that, to find optimization opportunities was just too hard. So we backtracked out of that effort and decided to start again. Let's go to part 3 of this talk, hope. I've spent some amount of time convincing you that compiling R is really hard and that, more often than not you'll fail. I want to leave you on a somewhat hopeful note. So the first, how can one hope to compile a language like R? And the general approach that we're following is speculative optimization. Basically, the idea is we're building a compiler that will guess what is the likely good code for a function, and if it guesses correctly, that function will run fast. If it doesn't, it has to undo its work, de-optimize the code and run slower, and then try another guess. That's a fairly well-known approach in just-in-time compilation. And this graph here is just to give you sort of a visual anchor for that idea. So this is the measurement of the execution time of a simple task in this case written in JavaScript. So every point in the graph, there's over 1,000 repetition of the same task, is the same task performed again and again in the same process. And what we see is on the left, the first executions are longer because the compiler doesn't know yet what you want to do, so it runs unoptimized codes. And then gradually the program goes faster, and we have these times where sometimes the compiler makes a wrong guess, so performance decreases, and then it increases again. And finally, around 250 iterations of the benchmark, we reach a roughly stable state. So this is data from a paper by Barrett et al. At UPSLA 17, and it sort of nicely shows the way compilers learn and improve performance as the program goes along. And this is generally the general idea behind what we're doing. We're doing speculation and coupled with the optimization. And the box here gives you some references. So this work has roots in the 70s and has been mostly worked on in the early 90s on the self-programming language, and this influenced Java and JavaScript and most highly optimizing just-in-time compilers. So what are we doing? What is our fourth attempt to compile R? It's a new just-in-time compiler. It's called J. And what J is a drop-in replacement for the bytecode compiler in GNU-R. It uses LLVM as a backend for code generation, but it performs a large number of optimization on its own intermediate representation. So we've learned from our previous attempt, we do a lot in a representation that is close to R. It's called PIR, peer, and then we drop down to LLVM, and LLVM generates the code for us. And what is interesting about our design is we have multiple versions for every function. So every function is compiled many times for different calling contexts. And what we can do is we can, this way, each time you have a different environment, we can generate slightly different code. And all of these are optimized for different contexts. To give you a very sort of rough idea of what we can do and how this looks like, imagine this function G on top of the screen. It's a function written in R, it has a local variable A, and it has a local function F in it. And then the last thing that G does is it calls F with argument 2. So what would the unoptimized J code look like? Well, we would generate 3 unoptimized function, G, which is shown on top, then PR0, that's the code of the promise passed to the call to F. So here we're calling F with the number 2, so the promise loads the constant 2 and returns it, and then the body of F. And our compiler is able to perform optimizations on this, so we can look at the code of G, and we can find out what is the value of F, and we can inline the body of F. And then we will be also able to inline within F the forcing of the promise, because we know what the promise is going to be. So the first step is here inlining in G the body of F. And you can see that now we're not creating a new function, but we still have to create environments as before because our semantics requires us to. And then the last bit of optimization, we inline the call to the promise, and now we don't have any promise creation, any forcing, and the function is as simple as it can be. So this is just a taste of our compiler. And what we did is we have an upcoming paper at the UPSLA conference that describes some of our advanced optimization techniques, and we've benchmarked against both GNU-R and the Oracle FastR, and here we just show some results. So we have 3 benchmark suites. The first is called Arweave FastS, and it's sort of small algorithmic tasks, and here we're between 1 and 23 times faster than GNU-R. Then the last benchmark is called SH, the shootout. That's the one I was showing you earlier. And here we're sometimes a bit slower than GNU-R and up to 46 times faster. And the middle benchmarks is the most interesting one because these are real-world codes full of micro operations. And one of and it contains only two programs. One of them were slower than GNU-R, and the other one were actually 26 times faster. So what is the takeaway? The takeaway is that we are moving closer to significant speedups. This is compared to the bytecode compiler, and we're slowly catching up to the FastR infrastructure, which isn't as backwards compatible as we are, and has much more effort put into it. So this is somewhat hopeful. When will this be finished? I hope that will take less than the next 10 years for us to see something that you guys can use. I will finish this talk by mentioning some things that R would need if we want it to actually reach performance levels such as Julia. The first thing, and this is something that one of the students in the lab, Avira Goel, is working, is the ability to add annotations to R. So the reason we need annotations is they can help us change the semantics in important ways. So for instance, it would be good to be able to let the compiler know that laziness is not required in certain position, or that some particular representations can be used for data types, and this can be sort of communicated by annotations. What Averell has been doing is he has a version of the R parser that can parse annotation statements. They can be ignored if you don't need them, but if you do, then you may be able to use them for better performance. The next thing is something that Alexei, another student of mine, has been working, is he's been looking at how to add types to R. So here we would hook into the annotation mechanism and allow programmers optionally, if they so choose, if they want it, if they feel that it's useful, add type annotations. And then what can you do if you have those type annotations? Well, there's two things we can do. We can find errors at compile time. So we can say you've defined this function, but here is a string and you're trying to add it to an integer, and that's not allowed. But we can also use it in the compiler as hints for what code to compile. So we would say, well, if you tell me that this is a function that takes two integers, I'll keep I'll have a backup ready, but by default, I'll generate code optimized for those two integers. And this will help us reduce the amount of code generated and better optimize code. And the last bit is potentially defining a strict subset of the R language. That is, there's lots of there are many features, reflection, that mostly people don't use. And we have data, and people really don't use those features. And yet, every implementation has to assume they're used anywhere. So wouldn't it be nice if we could say, well, this file has a strict annotation to it, and that means the compiler can assume that no funny business happens within it, and thus can compile code faster. So we have there are a number of papers that describe all of the things I've been talking about, and for the details I would recommend you to go to my website. And I would like to mention all of the people who have worked on this system. There's Sebastian, who's a PhD student here in Prague. Guido has his PhD and is back working in Argentina. Oliver is a PhD student in Boston. Jan is a PhD student in Prague. Gabriel works at INRIA. Mingho and Avirol are both PhD students in Boston. Amal is a colleague from Boston. Peter, Thomas are researchers in Prague. Florial is a professor back in the south of France, and Helena is a researcher position in Germany. And without all of them, none of this would have been possible. And with that, I thank you, and I welcome any questions.